Okay, the bell work today says, what is the mass of 1 mole of hydrogen peroxide, which is H2O2? And so what we need to do first is find the molar mass of this compound. So hydrogen has a value of 1.0, and oxygen has a value of 16.0. There are 2 hydrogens and there are 2 oxygens. So I have 2.0 grams for hydrogen, and I have 32.0 grams for oxygen. So when I add it up, my molar mass is 34. And now I can throw that into my conversion. I have 1 mole of H2O2 for every 1 mole of H2O2. I have 34 grams of H2O2. And so what you'll notice is that there's 1 on the top and a 1 on the bottom, so this really isn't going to change my answer. It's going to be 34. And it makes sense, because if I have 1 mole of H2O2, the molar mass is going to be my total grams. That's the conversion, 34 grams per 1 mole. So it makes sense that my answer is 34 grams of H2O2. For the other one, we already have the molar mass, so I'm going to start out with 10 moles. And then that is also H2O2. We haven't changed compounds. And my conversion factor is the exact same. For every 1 mole of H2O2, I have 34 grams of H2O2. And in this case, 10 times 34 is going to give me a value of 340 grams of H2O2. And there is the bell work. So we're going to move on to notes. This is going to be part 4. So up to this point, we have learned about the mole diagram. We have talked about converting representative particles into moles, and again, representative particles are molecules, atoms, ions, and formula units, using Avogadro's number, which is 6.02 times 10 to the 24. On the other side of the diagram, we've talked about converting mass in grams into moles using molar mass, which is a calculated value, which is when you add up the values of the periodic table. And finally, we learned the top of the chart yesterday, which was molar volume of a gas. And so if you have 1 mole of gas, you have taken up 22.4 liters of space. That's what that conversion was. We also talked about percent composition in the last video and how to calculate each element's contribution to the total weight. So that was part over whole, and you multiplied by 100 to get the percentage. So we have 2 things left to cover. One of them is called empirical formulas, and the other is called molecular formulas. So that's what we're going to look at in this video. So the first thing that we're going to look at is the empirical formulas. So again, we have empirical and we have molecular. This is going to be empirical. An empirical formula means the lowest whole number ratio of the elements in a compound. The word empirical means simplest, so it's literally the simplest formula that you can have. It may or may not be the same as the molecular formula. So let me give you a quick example. If I have H2O, I have 2 hydrogens for every oxygen. So this is the empirical formula because I can't get any simpler than this without changing the 1 oxygen into something that's not a whole number. What I can do is scale it up into something like this, H4O. Now obviously, it would be H4O2. So everything that I've done, I've basically scaled up by a factor of 2. What's written in red is not an empirical formula because it's not the simplest formula that we can have. So H2O here is our empirical formula because the ratio is as simple as we can get. Now, it's not the same as the molecular formula, but the molecular formula, H4O, we don't know much about this compound in particular, but this could be the right formula for some sort of other compound. So for now, we're just concerned with understanding the simplest ratio. So to find this, it's a little bit of a process. We have a 4-step method that is kind of used in order to figure out these problems. Step 1 says find the moles of each element. Well, what's awesome is that we now have a diagram and the 3 conversion factors to convert into moles of whatever we're given. So the first step is find moles. Second step is going to be to set up what we call a mole ratio. Okay, and I will explain that as we do examples here. Step 3 would be to simplify the mole ratio. And so what we're going to be doing here is dividing by the smallest number of moles that we have. And we're going to get some sort of number that we want to be a whole number. And if we don't, we're going to have to be multiplying by some sort of factor. And again, you're going to see this in an example, so just hang tight. And the last step here, we're going to have to use this mole ratio as subscripts in the formula. So whatever whole numbers we get, we're going to be placing them as subscripts. That's how we're going to figure out this simplest ratio. Okay. Just one other key that may help later down the road. If we're talking about percent composition, setting 100 grams of a compound as our basis is going to come in handy. So again, here are the rules. They're listed out. Until we see them in an example, this may be confusing to us. So those 4 steps were kind of wordy. We have a poem that you can use in order to remember it easier. The sooner that you get this poem memorized, the easier that you'll be able to do empirical formulas more smoothly and confidently. So here's the poem. It says, percent to mass, mass to moles, divide by smallest, and round till whole. And so these are short and condensed lines for the steps, but if you can remember this poem, you will be able to do the steps. So again, percent to mass, mass to moles, divide by smallest, and round till whole. So here is our first example for calculating empirical formulas. It says a compound is 79.8% carbon and 20.2% hydrogen. So I'm not given grams, I'm not given liters, I'm not given anything else. I'm given a percentage. And in a couple slides previous, it said that if I'm given the percent composition for these elements, which I am, I'm going to set a basis as 100 grams. So I'm going to say that my total mass is 100 grams, which means that these percentages here I'm going to be able to use in their numerical form. So what do I mean by that? Well, if my basis is 100 grams, that means that if I have 79.8% of carbon, I'm going to have 79.8 grams of carbon. And same thing for hydrogen. I'll have 20.2 grams of hydrogen if I have a basis of 100 grams. And that's okay to do. We can set that as the basis because we don't have any other numbers to go off of. So that is step 1 of our poem, percent to mass. That's what we just did. So number 1, we went percent to mass, and in the poem it goes percent to mass, mass to moles. So next I have to convert these numbers into moles, and I have to do both of them. So number 1, percent to mass. Step 2, mass to moles. So to do that, I'm going to need the molar mass for these compounds, and because they're just simple elements, I can go ahead and take those values off the periodic table. For carbon, 12.0 grams of carbon will give me 1 mole of carbon. This is our molar mass conversion. For every 1 gram of hydrogen, I'm going to have 1 mole of hydrogen. For carbon, I get a value of 6.65, and that is moles of carbon. And for hydrogen, obviously it's going to be the same because the mass is just 1, so this is going to be 20.2 moles of hydrogen. Okay, so step 1, percent to mass. Step 2, mass to moles. Next, divide by the smallest. So what does that mean? Well, what that means is I'm going to take whatever moles was the smallest, and I'm going to divide by that number. So in this case, 6.65 is our smallest amount. We're comparing 6.65 to 20.2. Okay, so in this case, I'm going to divide by the smallest. I'm going to divide by 6.65. And that is from carbon. So again, percent to mass, mass to moles. So this is step 3. Divide by smallest. And what do we get? So here, we're going to get exactly 1. And that's going to happen every time we do an empirical formula. Whatever the smallest is, we divide it by itself, and it's going to give us 1. That's going to happen. The other one, I'm going to get a value of 3.04. I'm going to round that. So step 1, percent to mass. Step 2, mass to moles. Step 3, divide by smallest. And then step 4, round till whole. So step 4, what we want to do is take these numbers here that we just got, and we want to round to the nearest whole number. Well, for this one, 1 is already whole. For this one, we want to round to the nearest whole number. In this case, we're right at 3. So I have gotten the whole numbers 1 and 3. 1 for carbon and 3 for hydrogen. So my 4th step is done. What do I do with these numbers? Well, I'm going to be using them in my formula. So what I write is carbon and hydrogen, and I fill in a 1 as the subscript for carbon and a 3 for the subscript for hydrogen. So if I was writing this out, my final formula would be CH3. I don't have to include the 1 there. But that's what I'm doing. I'm trying to find the formula, the actual formula of this compound. And that's what I did. So I have successfully calculated the formula, the empirical formula for this compound. Okay, and our last example for empirical formulas, it says find the empirical formula for a compound made up of 26.7% phosphorus, 12.1% nitrogen, and 61.2% chlorine. So I'm going to follow my 4-step process once again. First things first, percent to mass. So I'm going to take these percentages and I'm going to turn them into grams. And I'm using 100 grams for my basis. That's okay to do. And I will do that. So 26.7, and I'm turning that into grams of phosphorus. I have 12.1 grams of nitrogen and 61.2 grams of chlorine. Step 1, percent to mass. Step 2, mass to moles. So I need to convert these guys into moles. And I'm going to have to do that using my molar mass calculation. Phosphorus has a value of 31 grams per mole. And this is for phosphorus. I want to be specific here. Nitrogen has a value of 14.0 grams of nitrogen for every 1 mole of nitrogen. Chlorine has a value of 35.5 grams of chlorine for 1 mole of chlorine. And so, of course, this is step 2, and the answers that I get 0.86 1. I'm going to use sig figs here. This is going to be moles of phosphorus. For nitrogen, I get 0.864 moles of nitrogen, and I get 1.72 moles of chlorine. Okay, so step 3, divide by smallest. Well, in this case, I'm looking at phosphorus and nitrogen, and they're pretty much the same, but I am going to take the smallest. And if you're ahead of me, what you'll see is that when I divide those two out, I'm going to get about 1 for each of those compounds. So I'm going to divide by 0.861, divide by 0.861, divide by 0.861. The answer I get for the first one is 1. Obviously, we're dividing it by itself. The next one is going to be 1.00, so that's going to be 1 when we round. And then the last one, I get 1.99. Okay, so that was step 3, divide by smallest, and step 4 is round till whole. So 1 is going to be 1 here. This is already rounded to 1, but we're going to make it a whole number. And the last one is going to round to 2. So this is for chlorine, this one's for nitrogen, and this one's for phosphorus. So my compound, I have phosphorus, nitrogen, and chlorine. I'm going to take those numbers and plug them in for my subscripts. 1, 1, 2. So overall, my compound will be PnCl2, and that is my empirical formula.